Okay, so today we're doing the sum of a finite and infinite geometric sequence. We're going to start with the sum of a finite geometric sequence. That makes sense. We have a certain set of terms of our geometric sequence that we want to add up. This is the formula that we're going to use. S sub n is equal to our first term, which is a sub 1, or perhaps a sub 0. So be careful how the first term is indicated. And it's multiplied by 1 minus r to the nth power over 1 minus r. The numerator has the n in it for the exponent for r, so it's a good way to kind of memorize it. So in our example problem that we have here, so it is a geometric sequence, okay, and in it we want to find what r is, okay? Believe it or not, you can find out what r is by looking at the expression here. It's always the number or expression that's raised to the exponent. In this case, n is our exponent. R is 0.3, okay? We also need to find the first term of our sequence. So our lower limit is indicating if it's going to start with a 1, like a sub 1, or a 0, a sub 0. So we're going to take that and write that as our subscript. We're also going to plug it into the expression to figure out what that first term of our sequence is. So according to this problem, it's 4 times 0.3 or 1.2. So now we get to actually apply it into our formula here. So there was a formula for a finite arithmetic sequence. There is a formula for a finite geometric sequence. So we plug this all in. Remember, these numerator and denominator look the same, except the numerator has n, in this case 12, that we're going to use as the exponent for r. All right, you will end up needing a calculator for this one. The exact answer turns out to be a very, very large, fraction for its numerator and denominator. It's long to write out. If we're going to approximate this, please remember to round to 3 decimal places for your answer. So this is what it comes out to be. All right, so next. This particular problem, it's a little bit different. It's saying the sum of an infinite geometric sequence. It may seem strange to you, but we're going to go into it a little bit further in our next few lessons. But as long as your common ratio is between -1 and 1, it also can be written this way as well, then what happens is these sum, as you're adding up all your terms, they converge. That's the word that we use. Converge means to meet at a point or a place, so they actually do come together at a particular number. So that's why we're able to find the sum here. So this is the formula that we use. And if you look at our example, we can see that there's an infinity sign as our upper limit for our sum. So this makes sense. We're going to use this new formula instead. So in our example, we're going to first identify what r is, very similar to the last problem. So it's the number or expression that has the exponent. So in this case, it's 0.6. Now, 0.6 is between -1 and 1, or the absolute value of it is less than 1. So that's good. We also need to know the first term. Just like we did in a previous problem, we look to our lower limit, and it looks like a sub 1's indicating the first term. We have to plug it into our whole expression, not just part of it, the whole thing. And we find that in this case it is 4. Okay, so now the sum, and we don't need a subscript, the whole sum altogether, every single term you can imagine, is going to be 4 over 1 minus r. So it's 4 over 0.4, or pretty much just 10. That's it. Okay, that's supposed to be a 10. It looks a little bit like a 6. All right. Like I said, the subscript is not needed in the formula. I do see students put like an infinity sign here. It's really not necessary. It's understood that that is the entire sum. So now we're ready to do some practice problems. Let me know if you have any questions.